This is Dr.BDY Sunil, Associate Professor, Mechanical Engineering Department, Institute of Aeronautical Engineering, Hyderabad. In today's session, we will be learning about the moment of inertia of standard sections and composite sections. The course outcome of today's topic would be calculate moment of inertia and mass moment of inertia of a circular plate, cylinder, cone and sphere from the first principles. The topic covered would be moment of inertia of standard sections and composite sections. Topic learning outcome would be understand the concept of moment of inertia and mass moment of inertia involved in practical engineering problems. So first let us see the moment of inertia of plane figures. As we have discussed in the previous session, the procedure how to identify the moment of inertia of the regular sections, we will be seeing few formulae how we can represent the moment of inertia of the regular sections here. First one is the rectangle, where the IXX moment of inertia of this rectangle with respect to XX axis given in the figure. The size of the area, rectangle is given as height D and width B here, and the axis, reference axis which we are considering, XX axis, YY axis and AB axis. So these are the axes which we are considering, and we need to know the moment of inertia of these this rectangle with respect to the axis. So IXX would be BD cube by 12, and with respect to Y axis would be DB cube by 12, and with respect to AB is BD cube by 12. So remember, these are the formulae for representing the moment of inertia of the regular rectangle. Now coming to the hollow rectangle, you can observe here hollow rectangle is a rectangle which doesn't have a material in between. Okay, so there may be two rectangles considered. Here the material is not present, but here the material is present, right? So we need to consider the rectangle having the area which is having the material. So the moment of inertia with respect to XX axis and YY axis is same here. Only thing is we will be subtracting, we will be removing the moment of inertia of the hollow rectangle from the total rectangle. So that is the procedure that we considered, and that value would be BD cube minus DB cube, BD cube by 12. So small BD and uppercase letters BDs are the values of the lengths and breadths of inner hollow rectangle and outer regular rectangle. Now coming to the triangle and circle, again you need to consider the axis with respect to which the moment of inertia are considered. The base axis and the centroidal axis here. So the moment of inertia with respect to XX axis is BH cube by 36, and moment of inertia with respect to AB base axis is BH cube by 12. So the size or the shape of the given regular section should be considered, and the reference axis should be considered. Then coming to the circle. Circle has got this XX axis and YY axis through the passing through the centroidal axis. So the value of IXS and YY will be same. Why? Because it is symmetrical totally 360 degrees. So the value would be pi d power 4 by 64, or we can write pi r square, pi r power 4 by 4. If you observe carefully, the units of this moment of inertia would be length to power 4. Now similarly, if we take the hollow circle, that is we need to subtract the inner non-material condition. So the value of, again it is symmetrical about 360 degrees. So moment of inertia with respect to XX and YY axis would be pi by 64 into d power 4 minus d power 4. And semicircular lamina, again the IAB value is equal to IYY. Okay, IAB value is equal to IYY, and that value would be pi d power 4 by 128. That can be written as pi r power 4 by 8. Also, IXX will be obtained as 0.11 r power 4. So these are the moment of inertia of plane regular sections. And coming to quadrant, IAB is equal to IAC, that is equal to pi r power 4 by 16. You need to remember only one thing: the moment of inertia with respect to which axis is very, very important here. Moment of inertia of any axis which you consider, that axis moment of inertia is forms a key point here. Then for composite section, moment of inertia, till now we have seen for the regular sections, and for obtaining the moment of inertia of composite sections, like two or more regular shapes that are involved in a single given lamina, then how to identify the moment of inertia? As we have done it for in the centroid part also, here also we need to consider some procedure for obtaining this value. So what we will do is identify the x-axis and y-axis of the complex figure. If not given, create your axis by drawing the x-axis and y-axis on the boundaries of the figure. Okay. For any figure that is given, you first have to fix the reference axis. Then identify and divide the complex shape into basic shapes for easier computation of moment of inertia. When solving for the moment of inertia of a composite area, divide the composite area into basic geometric elements like rectangle, circle, triangle, etc., for which the moments of inertia are known. You can show the division by drawing solid or broken lines across the regular shape. Label each basic shape to prevent confusion and miscalculations. Now, solve for the area and centroid of each basic shape by creating a tabular form of the solution. Obtain the distances from the axis of the centroid of the whole regular shape before continuing to the computation of the moment of inertia. Always remember to subtract areas corresponding to holes. As you have done for the centroids, here also you need to subtract the values for the holes. Determine the distances h1, h2 and so on from the centroid of the composite section to the centroid of each part. Next step is to, once you obtain the location of the centroid from the axis, proceed to the calculation of moment of inertia. Compute the moment of inertia of each part about its centroid, that is Ig1, Ig2 and so on. If the centroid of the basic shape does not coincide, it is necessary to transfer the moment of inertia from that axis to the axis where the centroid of the compound shape is located using the transfer formula for moment of inertia. The moment of inertia with respect to the any axis in the plane of area is equal to the moment of inertia with respect to a parallel centroidal axis plus a transfer term composed of the product of the area of a basic shape multiplied by the square of the distance between the axes. So compute the values a1 h1 square, a2 h2 square and so on. Compute moment of inertia of given section from Ixx is equal to Ixx1 plus Ixx2 and so on. Then you substitute the values of Ixx1 as Ig1 plus A1 Hy1 square plus Ig2 plus A2 Hy2 square and so on. Similarly, for Iyy also, that can be taken as Iyy1 plus Iyy2, for which you can substitute Ig1 plus A1 Hx1 square plus Ig2 plus A2 Hx2 square and so on. You do remember these terms which are between the addition sign are the individual elements moment of inertia with respect to the centroidal axis and parallel axis. So once you summate or make the summation of all these terms, you will be obtaining the final moment of inertia. This concludes the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.